So this is question 55, and it states that a 200 kilogram weather rocket is loaded with 100 kilograms of fuel and fired straight up. It accelerates at 30 meters per second squared for 30 seconds, then runs out of fuel. Ignore any air resistance effects. And we'll be first looking at part A, which asks, what is a rocket's maximum altitude? So some important things to have before we start is here we can see that I'm going to label the first part of the problem as the acceleration upwards, so the first 30 seconds, and then the second part will be after the first 30 seconds when it starts to accelerate in the negative direction. So these will be our equations we'll be using. So there's 2 for velocity and then 2 for position, except the position ones are the same exact equation, just some parts removed because we can plug 0 in for some of these parts, which will eliminate them from the equation. So we can find our velocity at the end of our first 30 seconds by using this first equation because we have the acceleration and the time. So we know that our velocity at the end of the first 30 seconds will be 900 meters per second. With this 900 meters per second, we can, or then with our position equations, we can find the position at the end of the first 30 seconds, which we know that we can, our initial position was 0, so we can get rid of this first part of the equation. Our initial velocity and our initial time were also 0, so we can get rid of these parts of the equation. So we're just left with the 1/2 acceleration multiplied by time squared. So to find the position at the end of the first 30 seconds, which isn't the maximum position, but it gets us part of the way there, and we need that number for later parts. We can use the x equals 1/2 acceleration times time squared. So we do the 1/2, plug in the acceleration, which is 30 meters per second squared, and then the time, which is 30 seconds. When you do the 30 seconds squared, you get 900 times the 30 will get you to 15 or 13,500 meters. With that, we can now use our second velocity equation, which gives us velocity without having to use time. We just use change in y values. So we're able to plug in 0 because we know that our velocity at the maximum point of our maximum height will be 0 because it'll be at stationary. And then we know that our velocity initial is 900 meters per second squared. And then we have the times 2 acceleration change in y. So we know that our acceleration will be negative 9.8 meters per second because of gravity. So we're able to add all of, or multiply those numbers out so we can get down to our final part where we have our only variable as our final y height. So we're able to find that our final y height will be 54,826 meters, but with using significant figures, we can find that is 55,000 meters. So that's part A. And this graph just shows the part 1, the first 30 seconds of the rocket. And this is part 2, or part B, which asks how long is a rocket in the air before hitting the ground. So this is counting the initial 30 seconds where it's accelerating, and then a little bit of time from the time it stops accelerating, but it keeps on accelerating, but in the negative direction till it hits maximum height, and then all the way back down. So we can use the same formula that we used for velocity earlier, but we need to put it into a quadratic formula so we can find the roots, so we can find where we can equal 0 for position. Or sorry, we're using our position equations. So we need that in a quadratic so that we can find the roots, which is 0. So you can see that you have t squared, t, and no t here. That's the same as a quadratic in its standard form. So we're able to plug in our acceleration for A, our velocity times time for B, and then our initial position for C. And when you do that in your quadratic formula, you get two answers, one that makes sense, one that doesn't. You have a negative time, so we can discontinue that one. So you have 197 seconds, and you add your initial 30 seconds from your part one. So you can get 227.5 seconds, and with significant figures would be 230 seconds. And then this graph shows the position of the rocket for part two, and you can see that it doesn't start at 0, it starts at our 13,500 meters, and you can see where the negative time is, and then you can see where the positive time is. And this point right here shows us how long it was in the air for.